Hello, I'm Mark, and welcome to my Unreal Engine tutorials on how to add wings and flight control surfaces to your physics movement system. So in continuing with our physics-based movement series, we're going to be going ahead and creating systems that can be used to create uplift as well as down forces on your vehicle simulations, as seen here with my aircraft. I've got wings and a tail stabilizer, and the wings are providing the lift. So as our aircraft flies through our air, our simulated air, it's creating a shape. The shape of the wing is providing lift based on the amount of forward speed that is going over the wing. And then we're also going to create flight control surfaces, as seen here. So we'll create some ailerons so we can do loop-de-loops, and some elevators so we can pitch our aircraft up and down, as well as rudder actions. And these surfaces can all be used for both air as well as water or whatever other medium you wish to be moving your vehicles through, depending on what you're building. Alright, so as always, we've got a lot of ground to cover, and this is going to be a little bit math intense, since a lot of, bear with me, there's going to be a lot of equations here that we're going to be needing to put in. These are equations that I kind of found as I was doing research, digging through both the vehicle movement component as well as some other sources. So that I could then kind of reproduce this the way I kind of wanted to in this component. So without further ado, let's get started. So let's go ahead and just stop this simulation before we crash. And I'm just going to put the controller off to the side, and we'll just go ahead and minimize the demo. So, okay, so since this continuation, I'm going to go ahead and build this in the simulation configurations.h file. So this currently houses all the stuff that we're using for both our static thrusters as well as our gimbal thrusters, if you're continuing to follow along with what I've been doing. So we're just going to repurpose this file, and this is where we're going to add our flight control systems as well. So the first one I'm going to do is I'm going to go ahead and work on flight controls. And a lot of this is going to become a little bit repetitive since wings and flight controls are very similar in how they work. I chose some solutions chose to kind of lump them all together. I chose to break them out because I felt that wing stabilization is different from flight controls, and some of the solutions I saw, especially in the Chaos vehicle component, they tried to conflate it, and in doing so it created, I was actually seeing things where it could be either improved upon or missed opportunities, or worse, there were some bugs in there. So in doing so, I kind of took that out, decided to break things up. So I'm breaking things up into flight control surfaces, which is what we see here, which is rudders, elevators, and ailerons. And then we have our fixed wings, which are both going to be for both vertical wings, which can be, again, used for spoilers or wings on planes, as well as that horizontal fin, which when working with planes, you definitely need. And even with when I ported it back to the helicopter and put a little bit of horizontal stabilization, it actually helped the helicopter fly straight. This is going to help your aircraft fly straight, so versus having a little bit of a skid in there. So again, physics in action. That's the nice thing about working in this. You can actually start seeing some of those real-world principles playing out within your gameplay. So again, so we're starting flight controls, so rudders, elevators, and ailerons, and I'm using an enumerator so that this will allow us to map the inputs coming into the right systems. And also and it also has a double action of classifying this as it's going to act as a rudder versus an elevator versus an aileron. And we'll see that when we do the input mappings, as well as the force generation. And then the next structure, this is going to be a big one. This is going to be the physics control surface configuration or setup. So I'm just going to go ahead and bring all of this over first. And then we can just talk about that. So as you can see, it's rather big. Because there's a lot going on in here. So just starting from the top to the bottom. So what I've done is, again, we've got our tag as well as our enable. And we got the tag here because, again, this is something which you're probably which we're gonna have in an array structure. So you could have multiple types of control surfaces. You could have multiple rudders. You could have multiple elevators, ailerons, you know, whatever. So what we have here, so we have the tag name, we have the enable, we have the type. So here's our enumerator, and this is where we go and do the classification for our mappings. Negation, this is very useful, again, if you're trying to tie various control mechanisms into a single input source, right? So, and you'll see this if you're kind of working on things where you may have like submarines, where you've got dive planes on the front of the ship, but you've also got dive planes in the back, right? So one set's going to bring you up, but if you don't negate it on the other side of the center of gravity, you'll have one set of dive planes fighting the other set. And it could be the same thing if you've got multiple elevators on aircraft. So we want to be able to make sure that everything's going in the right direction. And also, if you're using vector control for thrusters, as well as having pitching up and pitching down, again, if things are on different sides of that center of gravity, then we just need to make sure that we're angling it correctly. So this is very useful. So we've got our is direction negated boolean there. We're reusing the force location configuration. So again, more reuse. Everything has a location on the mesh, especially when we're doing providing force at a point. And then we have how we want to calculate things. So first off, we have to have a surface area. So this is going to be the surface area of the flight control that we are using to manipulate the turning of the aircraft or the watercraft or the vehicle, which is using this. We have the camber. 9 times out of 10 or 99% of the time, camber is going to be 0, but there could be, so you may have some use cases where the whole wing actually moves versus just a piece of it, and that wing may have some lift, some natural lifting on there, so you could include that here. But most flight controls are kind of built into the wing, so you'd probably want the camber in the wing and not in the control surface. So that's why I've kind of defaulted this to 0. Max control angle. So this is the maximum angle at which you can your control surface is going to rotate, either up or down. So again, so it could have 20 degrees. So here by default, we're going to default it to 20 degrees positive or negative pitch. Or if it's a rudder, it would be yaw, right? Lift multipliers and drag multipliers. This is so that we can add some additional lifting and dragging if we need to. So if you needed to take into account other things on the wings, right, which could be helping to cause drag, or a natural source of drag, we can then just use the multiplier to kind of increase that. Same with lift. We could do that as well. So if you wanted to say, again, as we're turning, is it going to have a lifting effect or not? And that's kind of what this is there for. Right now we're setting it to 1 and 1, which means it's going to be turned off, but if we multiply anything by 0, it means it has 0 lift, versus a little bit. And then I also decided I want to include the pitch angle and the yaw angle offsets again, especially when you're starting to look at some of these more exotic planes, or even watercraft, right? Some of these are actually at an angle. And so when the forces are going over it, they're not going up, directly up. They could be going up and out, and that's usually to help provide, could be to provide stability by doing that. So again, we can account for that in your setup as well. And so I included both pitch angles as well as yaw angle offsets. And then, as always, I've got my the condition percent. Again, if you're looking to create gameplay in which things can happen, well, this will allow us to kind of set that off. So if the control takes bullet holes or a missile hit and degrades the performance of the control, then it would then technically, this is where we could then degrade its performance using the condition percentage. All right, so after that, we have some private variables. We have the density of medium. So this is actually going to be set through from the fluid dynamic system. And so if you're using a set variable, either water or air or whatever value it's going to be passed in. Or if you're using the curve, that curve value at that specific time will get put into, and if this is then used as part of the calculations for our dynamic pressure on the control surface. Angle of attack, again, control surface angle, that's going to be coming through, and then the airflow normal. And so again, this is the airflow going across that surface, which is then going to determine how much lift or how much turn that surface can produce based on the angle of attack and the angle that it's kind of going into the airstream. All right, as far as functions, we have some public functions, and then I have some private functions. So the private functions, these are all internal, so I just made them private. But these public ones, these are the getters and setters. So first off, we have our set control surface. So again, we're going to take an input, we're going to do a quick clamp on it to make sure that it's a clean number, which is between 1 and -1. So if it's 0, it means it's straightly aligned. If it's 1 or -1, then it's taking the maximum control angle. And if it's anywhere between 1 or 0 and 1, then we would just take a fraction of that control angle. And that's what this is doing here. So this is the control surface. We're going to clamp it, and then we're going to multiply it by this to get how much turn is in that control surface. And then set our density of medium. Again, this is going to be taking the density, putting that into the variable. And then finally, we have our get force. And so this is where we will take the velocity of the vehicle as it's traveling through a specific medium. And from that velocity, then we will make our calculations on how much force we're putting into that turn. Okay, so we've got some green squigglies here, and it looks like we don't have a green squiggly here, but we can fix that, so no worries. So let's go ahead and fix the green squigglies, and let's get the implementation done. So first off, I'm just going to go to show potential fixes, and let's start just filling this in real quick. Dynamic pressure. Drag. Lift. I'll just bring this over, and then we have get direction. All right, so let's go ahead and get started. And what I'm going to do is I'm going to start from the bottom and actually work our way up to get force, since these are the functions that are going to be used within get force to make its calculation. So first off, let's go ahead and work on the, actually, we also have the, do we have it? No, we're good. Just getting my bearings. All right, so let's see, calculate. So the first one is get direction. So we want to be able to get the actual direction of the get the direction that we want this control surface to be working in, and that is very important again, because rudders go in a different, go left to right, where ailerons and elevators go up and down. So we definitely need to make have a distinction there. So to do that, I'm just going to bring the code over. It's pretty simple. First off, we're going to create a direction vector like we do with the thrusters, zero it out. We're going to take our offsets and create a offset quat. And then from there, based on the enumerator type that we've set in our system, if it's an aileron or if it's an elevator, we'll be using the z-axis vector. And then we're just going to rotate it based on any offsets that are put in here. Otherwise, if it's a rudder, which is going left to right, which is, if this would be on the your axis vector, again, we're going to run it through the rotator to get the direction. Then we're going to check to see if we need to negate that direction. If we do need to negate it, we'll just take the direction and multiply that by -1, which will reverse it. Otherwise, if we're not, then we just return the direction back, and that is the direction in which we want the force to be exerted to help push our vehicle around as we're applying the control surface. All right, so that is the get direction. The next one is going to be the calculate angle of attack in degrees, and Visual Studio seems to have an issue with the green squiggly there. So I'm just going to go ahead and just bring this whole function over, and I'm just going to put this right there. So this is the calculate angle of attack function, which is right here, constant vector axis and a constant vector airflow is going in. And all we're doing is we're just taking these two values by reference, and then we're just doing a mathematical calculation in order for us to get the angle of attack that it's going into the wind in degrees. So again, this is important. This is the direction. This direction is being calculated here in get direction. And then this is the airflow, and the airflow, we'll get to that as we get up into get forces, but this is the velocity, or this is the direction of the airflow that's going to be used. And so again, to get the magnitude, we're going to do a vector dot product. So that's off the vector structure dot product, and we're going to be putting the axis and the airflow. So two vectors are going to give us a magnitude. And then from that magnitude, we're going to be using the math library and the fmath, and it's going to be using the A sign here. So we'll be using this function there, in which we then put the magnitude in, and that's going to return us the angle of attack in degrees. And then we're going to be using another fmath to take. So this will be radians, and so we want to convert it from radians into angle. And that's what's going to get returned there. All right, next up, again working from bottom to top, is going to be the calculate the lift coefficient. So this is going to be how much actual lift we want to put into our vector. And okay, and I'm just gonna fix that real quick. So that's the control surface here. So we have our control surface. So this is angle of attack time control surface angle. I think I changed that name. Yeah, that's why I did that. So let's revert this back real quick. And I'm gonna revert this back here and there. Make two small little changes, that way there's no confusion. Alright, so here's our angle of attack, there's our control angle. So here we want to use the angle of attack plus the control angle coming in. So these are two parameters that are being passed in, and our goal here is to get, again, a value coming back. So we have a peak value of 2, we have the total angle, which is taking angle of attack and the control angle, which gets the max angle, and then we're going to take the absolute of it, because this angle could be both either positive or negative depending on whether we're going up or down, and again whether this how that control surface works. So we want to take the absolute and then check against the absolute of the control angle surface times 2. If our total angle is greater than this, then we're going to return 0. And because if it's greater, then we're hitting a stall in which the system is just so far out of whack that it won't be adding any value to turning. So as long as we're within the bounds, and that's what's being calculated here, we're okay. If we're out of bounds, we're going to return 0. And then here again, this is an equation that I found when digging through the code. And how they were kind of looking at doing it, and it works, so I took it over. Again, it takes the total angle, and then it's multiplying that by pi divided by 2, or divided by 2. So half pi times total angle, right? And then divide that by the max control angle, and then what happens is we then want to take the sine of that, and then it's multiplied by the peak value. and that's going to return us a value of how much actual lift, and that's either lift going in one direction or the other direction, and that's what's actually going to be moving us around on that control surface. All right, so then there's also, because we're putting a control surface into the jet stream or the water stream, or the airstream, right? Then it's also going to create some drag. So we want to also simulate that drag effect as well. So to do that, I'm just going to go ahead and grab this. And again, control angle, because I want to be using the properties coming in. So again, it's going to take the attack angle and the control angle. Here, what we want to do is we want to take the angle and we want to reverse it. And the reason why we want to get the opposite, so if by using this, we want to get the opposite of this number. And the reason why we want the opposite is because we're creating drag, right? So we want to create we're here to create now a counter force on the on that control surface. And so that counter force is going to be based on the angle of attack plus the control angle again, which is the total angle. And then what we're going to do is we're going to divide that by the maximum control angle, as well as the absolute, plus the absolute control angle, which is coming in. And then once we have this value, we're going to multiply it by, we're going to say multiply it by 2, and then divide it by 0.05, and then multiply it by 2 to get the square. And then we're going to add 0.05 to it. And so that's kind of what we're doing here. And this is very similar to the way that the wings are going to work. Again, doing something a little bit different for the wings, but again, it's very similar calculations. So let me just minimize that, minimize that. I'm going to minimize this and minimize this. All right, so calculate dynamic pressure. That's pretty simple. All we're taking here is going to be the velocity squared, which is the velocity of our vehicle moving through a particular medium, and then we're going to take the density of that medium, and so we're going to take half the density, so we're going to take the density times 0.5, and then we're going to multiply that by the velocity squared, and that should get us the dynamic pressure. All right, and as we continue to move up, now we're ready to talk about getting the force to actually push the aircraft or the watercraft or the vehicle that is using this control system in the direction it needs to go. So I'm just going to go ahead and copy this. I'm going to just pull this over. Just going to minimize these since we don't need them. All right, so here's our first get force. So this is the getting the force for our control surface. So again, very similar to what we were doing in the thrusters. We first want to create a force, zero force. Then we're going to check to see if the wing's turned on or not. So if this control surface is turned on, then we want to apply that. Then we're going to take the airflow magnitude squared. So this is going to be the vector coming in. So in order for us to calculate it, we're passing in the velocity of the vehicle as it's moving through space, right? And then from that, we want to go ahead and take the velocity, square it. And that's going to be the airflow or the water flow or the flow magnitude squared. And then from there, we're going to do a check to make sure that it's not a small number. So this checks to see if we're actually moving or not. So we might not be, we could be very, very, very gradually moving, but if there's not enough airflow, right, then if there's not enough airflow, then it's eventually, to actually do anything, then it's essentially just zero. So that's what we're going to do here. And that's again, this is an Unreal Engine constant that we're using here, just like with the pi. And that's what they determine to be a very, very, very small number. So if it's a small number, again, we'll return a zero vector. Otherwise, if we are turned on and we're not a small number, then we'll go ahead and take the velocity and take the reverse of the velocity coming in, and that's going to be the airflow. Then we're going to normalize it. And then from the normalize, and then after we've normalized it, so normalizing the vector in place of it, you can kind of read that, what it does there. So it's going to check the tolerance. And then off the normalization, we're going to then first calculate the angle of attack in degrees. So we want to then turn this into the angle of attack. So again, we want to get the direction, right? So again, if it's up, down, if it's an elevator or an aileron, we want either the up or down, versus if it's a rudder, we want the left or right. And then we're also passing in the airflow normal. Control surface, so here we've got this total control angle. So again, this is the control surface angle that we're putting in through the input, and then if there's any additional camber that needs to be added, we can do it here. Otherwise, if not, well, we'll just take this value as is. Dynamic pressure, all we're doing here is we're going to calculate the dynamic pressure based on the airflow magnitude here that we've calculated. And then we're going to multiply that by the area, and that's where we're going to create this common value. And so this common value coming back is the dynamic pressure over a given area. And then we're going to then use that to multiply for our lift coefficient and our drag coefficient in the get force equation down here. So to do the lift coefficient, we've got our calculate lift right here, again taking our freshly calculated angle of attack, and as well as our total control surface angle. And then there's the multiplier, so we need to add a multiplier. So if you wanted to turn this from a wing that's giving us lift into a spoiler that's giving us downforce, then all you needed to do is just take, in the multiplier on the control, just make it negative, and instead of an up force, you can now turn this into a down force. And then on here, this is our drag multiplier. So again, just multiplying it. So if we needed to add if we needed to amplify whatever this value is, we can do that through the multiplier. And then here we've got our force. So this is how we're calculating the force. So we've got our direction. Again, this is important to make sure we get the force going in the right direction. Then we have our common times lift, and we have our common times drag. And then it's going to be added into the airflow normal as well. All of that gets calculated up. And then finally, we have our condition. This is the condition of the wing or the control surface. So, and so if it's 100% good, then we'll take 100% of the force. Otherwise, if it's damaged, we will take what's left. So if it's only good for like 50, if it's damaged to 50%, then we'll only take half. If it's 20% useful, then we'll only take 20% of this, returning it back. So this is how we can create performance degradation in gameplay. All right, so that should do it for our flight control surfaces. Just going to try and close this up a little bit. So let's go ahead and come back into our simulation configuration, and we'll go ahead and bring in the wings. So again, they're very similar. Very similar in calculations. Like I said, I like to split them out because I want to just separate the concerns. Flight controls are really about moving, where wings are really about going up and going down, or giving lift or stabilization. So for wings, again, there are two types. There's vertical wings and horizontal wings. So in order to configure the setup, we need to determine which direction we want the force to be going in. Is it vertical or is it horizontal? So there's our enumerator there. And then another thing that I decided to do with wings, because again, you've got a lot of these modern aircraft, they actually have the ability to change the profile of the wing. So anything from, say, flaps, right? So different flap systems. Some flap systems just put a downforce, which just create drag. Others will actually change the entire shape of the wing, right, in order to create upforce or downforce. And then other aircraft, they actually have it so like variable geometry, like the swept back wings of the F-14 Tomcat. you know, again, that would change the geometry, which changes the surface area and everything else. But then you've also got things like, say, the A10 Warthog, right? It actually has 3 geometries in there. It has one for speed, one for maneuverability, and then it has one flaps down for landing. And they all are there to change the characteristics of the aircraft's wing. So what I've done is I've actually gone ahead and broken this information out. So unlike with the control surfaces where they're pretty much static, here we can actually create individual profiles on that stabilizer. And it's usually on the wing. You don't really see these on maybe the horizontal, so I'm only limiting it to the wings. But this way you can actually change that shape and change the values associated with it to give it different unique characteristics. So that's what I'm doing here. So that's what this guy is for, and we'll see how that's going to be implemented within the wing structure. So then next is the actual structure, which is going to allow us to do our wings and our vertical and horizontal wing setups. So again, I'm just going to bring this over, and I'm just going to grab the API tag, put that there. Okay, so this is our setup. So, and again, this works within an array when we bring it into the component, but for now, so this is our physics foil. I'm calling it foil because this could work for air wings, race cars, but it could also work for underwater wings as well. So the first thing we're going to do on the constructor, by default, we're going to go ahead and create a physics foil setup. We know that we need that setup, so we're just going to do that. So for every one of these that we add into our component, it'll also create a default physics foil setup as well, which is this guy up here. Yep. And then, as always, tag name, because it's in an array, so we can find it. Enable, if we need to turn it on or off. Force point location. So again, this is where the location that we want to generate that lifting force or down force is going to be, or that stabilizing force. That's where that's going to be. And then we have our foil setups, and this is an array right here. So we can set up shapes within that array. And then we have our enumerator, which is telling us, is this a vertical or is this a horizontal wing? And then, as always, control our condition %. Again, if you're creating a game in which bullets are flying and punching holes in wings, well, holes in wings do degrade the performance, and so this is where we can actually degrade the amount of force that is being generated through that. So now we've got our functions. So we have our public functions. So we have our getters and setters up here. And then again, we also have our private functions. Our private functions look very similar to what we did for the control surfaces, as well as the values down here. The only addition is our current foil shape, which is the foil shape that we would be using to make our calculations. So as we kind of walk through this, I'm just going to go fix this real quick, and we'll just import the other functions as needed. I'm just going to move this down to there. So this is our set foil configuration shape. So first off, we got our get foil. So this get foil shape. So this is going to be used to allow us to tell us which foil shape, and it's public because we may need it in the vehicle itself to say which shape we're currently in. But it's also going to be used internally as well, so when we make the calculations. So what this is going to do is here's the foil shape array, and this is the current foil shape that we're going to be pulling out. We have the set foil shape, as we just kind of fixed it, and we'll get into that, and that's going to be allowing us to set it. I'm just going to call it position, but again, it's just all it is just an index for which one of these we want to use, which is currently in the array. Again, set density medium, it's the same as we're doing for the control surfaces. Get force is going to work very similar to again control surfaces, And then we have this get center of lift offset. So this is very useful when it comes to wings, because as you get faster across that wing, technically the center of lift will actually start to move back from the original. So you have your starting point, so as you're kind of like flying at low speeds, your center of lift might be slightly forward, but then as you get faster, it's going to be creeping back into the back of the wing a little bit more. So we can kind of simulate that a little bit here. All right, so let's go ahead and start to get the implementation done. So we have our set current foil, so let's go ahead and do that first. And I'm just going to bring this over. So what we have again, so I'm actually going to do a check. First off, I'm going to say, is this a vertical? If it's a vertical, then we'll start to accept the position. And the reason why I did this was because I don't really, unless you, it's a real edge case if you want horizontal as well as vertical, but mostly this is going to be done for vertical. So if this current setup is a vertical, then we'll go ahead and accept the position, and then or the index, right? And then what we'll do is we'll check to make sure that the index, if this is a valid position within the array, and if it is, then we'll set the current foil shape to that position, and that's what we'll be using. So that's all that does there. I'm going to go ahead and again start from the bottom and work my way up. So we'll start from here and work our way up. And since Visual Studio is not giving me any cues, then I'm just going to go ahead and just bring these functions over wholesale. So get direction's a little different on this one, since we have the concept of vertical versus horizontal. So I've just got a switch case here. And so what we're going to do, so again, we have the ability to have a pitch angle offset or a yaw angle offset, and as you can see here, there's our get foil shape. So again, this is where we can get that foil shape based on what we've set it to up here, and that will get the offsets for us and put it, and then create our quad rotator. And then from there, we'll then go ahead and determine whether we're on the x-axis or on the y-axis, depending on if we're vertical or horizontal, and then that should rotate, get us the exact vector rotation for us for this force to be applied. Otherwise, if it's neither this or neither that, then we return a z-axis. We'll just default to z-axis vector, but since there's only 2 in here, we should never get down to here. All right. So now that we've got that done, so that's our direction. The next thing is going to be our, again, calculate angle of attack. So I'm just going to put that up here. And it's pretty much the same as the other one. Really not going to explain it too much. It's using the same equation, but again, dot product. This axis is instead now going to be whether it's a wing or a fin stabilizer. And again, but the airflow is the same. So we're using the same kind of calculation there. Nothing's really changed. Calculate lift. I'm just going to minimize these. So calculate lift. I'll keep that open. So again, the same idea. The only difference is that again, we're going to go into the force shape, and then instead we're going to be pulling the stall angle instead of the max control angle. But everything else is pretty much the same. So there's our shape, there's the stall angle, same kind of calculation. And then after lift, we've got drag. And once again, the key difference here is we want stall angle on the wing, and then we have the get, and that's coming from our get foil shape function. But everything else is pretty much the same. And then calculate center of lift. So this is a new one, and this is going to be used for us to be able to calculate the center of lift in when we're, so as our vehicle is moving through the air, we want to again see where exactly we want to put that center of lift. or downforce, right, if it's a spoiler on a car. So again, this is going to be taking the angle of attack that we've calculated. Again, stall angle coming from our foil shape setups. And again, here, so if the angle of attack is greater than the stall angle, then we're going to say angle of attack minus the stall angle plus 10, times 10 plus 20, right? And then that's what we'll return. Otherwise, if the angle of attack is less than, then we'll take the stall angle minus the angle of attack, multiply that by 20, and then divide that by the stall angle plus 20. So that's how we're going to be calculating the center of lift. And then finally we have get the center of lift offset. So the center of lift offset is actually using the calculate center of lift. So with this, again, and this is only going to be on the x-axis, so we're only interested in getting that vector moving forward or back. So what we're going to do is we're going to calculate the center of lift, and then we're going to subtract 50, and then we're going to divide that by 100, and then that's going to give us our x value. Our x value is what we're going to plug in here. So then what we're going to do is, here's our force point, get location, and then this is the vector that, and this is the new vector that we're going to add, and this is in the x position, right? So we're just going to add these two together, and that's going to get our center of lift and offset it, and this is going to offset it by the attack angle and speed. Okay, and then two more. Again, dynamic pressure, nothing's changed here. Same way we're calculating on the control surface, we're just going to calculate it that way. And then get forces. Let's bring this one in. So this is us getting the force. So again, we're taking the velocity in. Again, checking to see if the wing is turned on, making sure that our magnitude is, we have enough airflow movement over that surface in order for us to do a calculation, a meaningful calculation. And then again, velocity, we want the velocity going in the other direction, normalize it. And then angle of attack, there's our calculate angle of attack. Again, the same way that we're doing it. The only difference is we have different shapes of wings, and we've got to make sure we've got a different direction. Again, common. Again, this is coming from the shape of the wing, and then calculated by the dynamic pressure. So this is our dynamic pressure for the multiplied by the area of the wing, and that's what our common value is. And again, it's being used for lift and for drag. And then the same way for calculating the lift and the drag multipliers. The only difference here is that we're just getting the camber from the foil shape, and we're getting the multipliers from the foil shape that we specified. So there's our, there's the equation, nothing's changed there, and again, there's our condition, nothing's really changed there, and that's going to return our force. All right, so that should do it for our systems. For both wings and control surfaces. I'm just going to go and minimize these. So let's go ahead and move over to our traits. So because I want to have the ability to change the shape of the trait, of the wing I should say, I'm going to go ahead and add into our vehicle simulation state here. Right, so this is the current state that we're constantly updating, and I'm going to go ahead and make sure that we're also updating the current position of the foil, since that's very useful when we want, especially, and we'll be using that when we recreate the aircraft with the flap position. So I have one where the flaps are down, high drag, more lift, and then the flaps go in, and the aircraft has less drag. Or less lift and at low speed, and but a lot less drag, so it can move a lot faster. All right, so that's that, and that's the only thing we're adding into traits. That's the force shape, and so again, these are all the variables that we're constantly updating. So this is the current state of the vehicle, both on the GT, the game thread, and on the physics thread. Actually, all of this is going to be updated on the physics thread. This is only updated on the game thread because this is only set on the game thread. So that's where we update this. But again, this system's being constantly updated on both threads to make sure that we have the most current and up-to-date information. All right, so next let's move over to our simulation component and let's go ahead and add this all in. So first up, I'm going to go ahead and let's bring in our wings and flight control surfaces. So there's our full configuration there, and we're just going to put into an array, and there's our control surfaces, and we're putting into an array. We don't need to add any more includes since we're reusing the simulation configuration.h file. So that's all there. And again, just the same blueprint read only, edit defaults only. Very similar to what I did for the physics thruster and the gimbals, all under simulation. All right, so now that we've got that in there, let's roll down to implement our functions for implementation. So just like the thrusters, we do have some setup on the wings, or the foils and the control surfaces. So I'm just going to go ahead and add a new function in here. So this is create control surface setups. We'll do it for both wings and for foils and for control surfaces. We will be doing some updates to apply inputs, but we'll leave that there for now. And then the only other things I want to add, I'm just going to append them to the bottom here. We've got our apply foil forces. So this is for our horizontal and vertical stabilizers. Apply control surfaces. Again, this is for our ailerons, rudders, and elevators. And then I've got a common function that's going to be used between both, and this is to, again, get world velocity at the point. Since we're using the velocity in order to calculate that, in order to calculate how fast the air, we're going through a medium, right? So this function will help us get that information for us. And then finally, under the under our public, I'm just going to go and add in the foil shape. So under set medium, I'm just going to go add it here. So this is our foil shape. So this allows us to go and change which foil setup under the wings we want to use. And I don't think that there's anything under private that I want to change. Nope. Everything else here stays the same as far as the inputs. All right, so let's go ahead. I'm going to go ahead and just fix all these green squigglies real quick, and then we can move over to implementation within the components. And that one. All right. So let's moving into implementation. So first up, just like we did in Begin Play for our environmental and our thruster setups, we're going to need to do the same thing. So we have our create foils and control systems setup. So I'm just going to put that there, right underneath thruster setup. So I'm just going to add that there. There's our new function. And then for our new function, I'm just going to go and bring this over. Again, it works the same way that we did for thrusters. We're going to be looking for that bone or socket name, and that's what we're going to be using to create our location of where we want it. Well, and if there isn't, we'll just take the offset without the bone socket. So that's how, that's what we're gonna do to kind of map all that up. And again, it's reusing our function which we did here. So again, our function, if it's a skeletal mesh, we do it one way. If it's a static mesh, we do it another way to try and get that information. Otherwise, if it's neither, well, we've set up the blueprint wrong and we'll bring back a 0 anyway. All right, so that's our create control surfaces. All right, next is input. So as you can see here, we have our thrusters, we have our gimbals. So I'm actually going to then now add in our control surfaces. Since we only need it for control surfaces, we're not doing this for wings. So control surfaces, pretty much for rudder, what we're going to do is we're going to take the input coming in on the yaw, and then we're just going to reverse it. So we're automatically going to put a reverse in on the yaw inputs, and we're just going to set it that way. And then for simulation, for pitch going up and down, we're just going to take it as is, put it in if it's an elevator. And then if it's an aileron, right, then we're going to check to see which aileron it is. So when we pull, so if the aileron's on the left side, right, we're going to then put it as control input one way. If it's on the right side, we'll put the control input on the other side, and we will reverse it using the negative sign right there and right there. Okay, so that should be it for input controls. So next, we're now in the update simulation. So this is where all the magic happens on the physics thread, anyway. So on the physics thread, we're going to first apply the inputs. We're then going to update the input simulation, again, right here and right here. These are the two functions. There's the foil, there's our control surface, there and there. And I'm just going to put it in between that and the apply torque. And this is just really any additional torques which are running through the torque control system. If we're using that, if it's turned on. All right, next is apply thrust forces. Nope, we don't need to do that. We already applied it. One thing I have changed though in applying the thrust force, and I will bring that up. So previously I actually had this kind of sitting in here and I zeroed out the mass. I have changed it a little bit as my thought has evolved, and I've felt that while if you're a car on the ground you can get away with just X and Y, but if you're going in 3 dimensions like an airplane, a helicopter, a spaceship, or a boat, or even a submarine, right, or a submersible, then technically you're going in 3 dimensions, and at that point it does matter. And even a car, technically, that Z should matter. It's it's the difference between having a vehicle that is its center of gravity is top heavy versus having a center of gravity which is low to the ground. So I actually took that out because I felt that it is relevant. And then I just moved this up here since we don't need to calculate it on each time through the loop. We just need to calculate it once on the tick. So that's kind of where that is. So again, that's just a small change, and I'm again going to use that same. We're going to apply that same idea to the foils and the control surfaces. So I thought I'd just bring that up real quick. All right, so apply foil forces. So this is our wings. So I'm just going to bring all of this over. Okay, so looks more intimidating than it really is, since we've already covered the heavy lifting. So first off, altitude. Again, this is important, especially if we're for our density system. If we're using a curve, if we're not using a curve, not quite as important. So here's where we're going to get our altitude. This is where I'm going to get our density. And we can just calculate that on the tick and then apply it to all the surfaces. So that's why it's on the outside of the loop. And then, again, this is going into a fluid dynamics system to get our density value. And then from here, we have our center of mass. Again, handle center of mass. And so that's going to bring us that vector there. And again, we're not zeroing anything out. And then we are going to iterate through our 4 configurations. I'll just set it to C. And then first off, we're going to set the current full state to whatever the simulation state is. So this is our current force shape that we want to use. So we're going to set that. And then from there, we'll make our calculations. So set density, and we're also going to set the density medium. We're going to get the world location. And that's going to be from the transform position. And then this is where we're using that new function, get center of lift offset. And then again, we're going to take that center of lift offset, and then we're also going to bring in the center of mass, any changes from the center of mass as well. And this is center of mass. I think this should be the world center of mass. And then we have our vector test here. And then from here, we have our center of lift. Center of mass again. Actually, I'm using this as a vector test because I wanted to actually test this out. You can go ahead and use this. I wanted to see where that lift was and how that was being applied, and this actually will show you as you're kind of getting, as your vehicles are getting faster, that vector, that center actually moving away. So I'm just going to go comment this out real quick. But if you wanted to use it and you wanted to actually see that center of mass actually moving in real time as you're flying with debug turned on, you can kind of see that. It's not huge amounts, but it's enough, and it can be enough, especially when working with the center of gravity, to kind of shift the change in the characteristics of your aircraft. So that's what that's there for. So once we've got the world location, getting back on track. So we've got the world location. Right, that's our world location. So here we need the velocity. We want to simulate the velocity, which is what we're going to be using to get our local force. But it's also the velocity, which we're going to be using to get our local force here. So we're going to take the velocity. So this is the simulated world transform, inverse transform again. And this is where we're going to be using our new function, get world velocity at point. We're going to put the handle in and the world location. So again, remember, this is the world location, not the relative location of where all that is. So then this is the local velocity based off the world velocity at point. And then from there, we'll get the world velocity, and we'll put the velocity in, and here we're going to use this physics simulation, and we created a centimeter to meter scaling. So what this will do is it will then just make a conversion. So we take this and turn this from centimeters, which is what's coming out of Unreal, and turn it into meters so that we can use that. That's how we're calculating. And then from here, we get the local force back, transform that local force so that the force is, is relative to the relative rotation of the vehicle. And that's going to give us our world force, rotated world force. And then from there, we just add the force at position. So this is our rotated force at position. And we're then going to convert it back from meters to centimeters, since Unreal Engine prefers it, it wants everything in centimeters. And then there's our world location there, and that's the position, that's the place in the world where we want that force to be applied on our vehicle. Okay, I'm just going to go and skip over the control surfaces real quick, and I'm going to go into this world velocity at point since we're talking about it. And it's kind of a rather unique function that I kind of took from the Chaos wheeled vehicle system, and what it does is it's actually calculating off the center of the relative center of mass, and you can actually, if you want to put a debug in there, you can actually see this relative center of mass is actually shifting slightly as the shape of the vehicle starts to move. So as you kind of turn, especially in skeletals, as you kind of turn your control surfaces up, down, left, right, is actually going to then start to pull and push on that center of mass a little bit, because you're now taking it out of whack. And so what this does is it actually takes that into consideration. So it's going to get the world center of mass. So this is again the world center of mass position. And then what it's going to do is it's going to take the location, which again is the world location and the world center of mass location, and it's going to go ahead and take out any differences. So there's our diff. But then we're going to do a cross product, and this cross product is being done on this cryptic W function. And what this cryptic W function is, this is actually the relative center of mass. So it's not the world center of mass, it's actually the relative center of mass. And this is when, again, if you wanted to, you could kind of play around with this and kind of put it and debug it out, and you'll see as the skeletal moves. And again, it's not massive amounts of change, but it is enough to kind of adjust and show little bits of inertia as the characteristics of the vehicle does change. So, and that's kind of what we're doing here. So then what we're doing is we're creating that cross product difference, and then we're subtracting that from the actual velocity. So that's what this V is. Again, kind of cryptic on this handle. Really wasn't intended for us developers. You kind of have to play around with it to kind of see what it actually does. But yeah, that's kind of what we're playing with. So that's kind of what we're doing here. Otherwise, and then again, if this handle is a invalid, we'll just return a 0 vector. All right, so that is the get velocity at point. And so that's kind of what we're doing there. We're really just trying to hone in that velocity and then make subtle changes based on any shifts in that relative position. All right, so then let's move back up to apply control surfaces. So for this one, I'm just going to do a quick check. Say if handle. So again, like everything, we want to make sure that the handle is valid. If this thing is not valid, then and we try and do it on anything on an invalid handle, the system will crash. So we don't want that. So what we're going to do here is, again, I'm just going to copy this over. So this is for control surfaces. Again, calculate the altitude. Again, everything is relative. If we're using a curve, we need the altitude. If we're not using a curve, then we'll just get the actual the hard value. Again, center of mass, the center of mass. That's what we want here. And then again, we're going to iterate. Now we're just going to iterate through the flight control surfaces. So a little different. We're just going to set the density to medium since we don't have any foil shapes. And then we'll again get the world location, transform, get the location, center of mass. Again, we want to use, very similar. Pretty much this is very, very similar to what we're doing up here. The only difference is it's just slightly, it's all coming from a different system, different information. And then get force velocity, again, centimeters to meters to do the calculations, and then we transform it back from down here, from meters back to centimeters, so that we can add the position in our thing here. So very similar to what we do for wings. Again, the only difference is we just don't have this shape change. All right, so I'm just going to minimize that and minimize that. And so then lastly, the only thing we need to do now is just have a way for us to change that shape. And that again is being done from within the vehicle on the game thread. So there we are, simulate our current fall shape. All right. So with all of that information there, we should be able to make sure everything's saved. And once everything's saved, we should then be able to compile it, make sure we have a good compile, and then we can move on to then testing out. So let's go ahead and bring up the physics movement live. Okay, and compile. All right, good compile. Alright, so I'm going to go ahead and stop this video here. We've already done about an hour going over the systems. So what we'll do in the next video is we'll pull out the aeroplane, and I will leave a link to that fighter that I found on Fab in the description below, as well as a link to the playlist, you know, and if there's things that you kind of want to go back to, I'll leave that link there too. But yeah, so we'll in the next video we'll go ahead and add these control surfaces to the jet fighter, but then we'll also go ahead and add them into the helicopter as well, because when I added them to the helicopter, it definitely did change some of the characteristics, some for better, some for worse, or interesting characteristics, I should say. But we'll add them back in because it did really help the helicopter fly a lot better with that control surface. Alright, so as always, if you like what I'm doing, feel free to like and share my videos, as well as subscribe to my channel, and I will see you again in the next video. Cheers, have a good day.